Picture a point in space where gravity is so intense that even light cannot escape its grasp. A place where the very fabric of the universe twists and bends into something beyond our everyday understanding. This isn't science fiction, it's the reality of a black hole, one of the most mysterious and compelling phenomena in our cosmos. These cosmic giants don't just consume matter, they warp space and time, challenge our understanding of physics, and ignite our imagination with possibilities that once seemed reserved for fantasy. What if I told you that some of the wildest ideas about black holes aren't just speculation, they might be true? Today, we're setting off on a journey through 25 astonishing theories about black holes that could reshape everything we think we know about the universe. From the mind-bending concept of wormholes offering shortcuts across the galaxy to the startling idea that black holes might not be entirely black after all, each theory opens a door to a deeper mystery. We'll explore how these enigmatic objects could be gateways to other universes, or perhaps even cosmic recycling centers for matter and energy. Some theories suggest that black holes hold the key to understanding the birth of galaxies, while others propose they might be intimately connected to the nature of time itself. This is more than a list of ideas, it's an invitation to wonder, to question, and to marvel at just how strange and magnificent our universe truly is. Whether you're a long-time space enthusiast or simply curious about the frontiers of human knowledge, there's something here to captivate your imagination. So settle in and open your mind, because we're about to dive into the depths of space and explore the theories that could change our understanding of reality forever. But what if that point of no return isn't an end at all, but a beginning? Our first theory propels us into one of the most thrilling possibilities in all of cosmology. The idea that a black hole could be a natural wormhole, a cosmic shortcut or gateway to another universe. This concept isn't just pulled from a sci-fi novel. It has roots in the very equations of Einstein's theory of general relativity. Physicists Albert Einstein and Einstein-Rosen found that the math describing a black hole could theoretically be extended to form a bridge connecting two different points in spacetime. This hypothetical tunnel became known as an Einstein-Rosen bridge, and it offers a breathtaking vision of interstellar travel, linking vastly distant regions of our universe or even entirely different cosmic realms. The journey through such a passage, however, would be anything but a leisurely cruise. The initial approach to a black hole's event horizon presents the first monumental hurdle: spaghettification. This is the gruesome yet accurate term for the tidal forces that would stretch any object into a long, thin stream of atoms. The difference in gravity between your head and your feet would become so extreme that you would be pulled apart like taffy long before you ever reached the central singularity. This alone seems like a deal breaker for any would-be traveler, but theorists suggest that for a truly massive black hole, like the supermassive ones at the centers of galaxies, the gravitational gradient at the event horizon might be gentle enough to potentially cross without immediately being shredded. You might just survive the entry. Assuming you could pass through the event horizon intact, the real mystery begins. The interior of a black hole remains one of the greatest unknowns in physics. Our current laws break down at the singularity, the point of infinite density. Some models suggest that instead of ending at a singularity, the bridge could theoretically connect to a white hole in another universe or another time, a region where matter and energy are expelled outward rather than sucked inward. You wouldn't simply be falling into a pit, you'd be transiting through a tunnel with an exit as mysterious as the entrance. The implications are staggering. A traversable wormhole could make interstellar exploration possible, connecting points light years apart in an instant. It could even provide a passage to a completely different universe with its own physical laws and constants. Of course, the challenges are as immense as the promise. For a wormhole to be stable and traversable, it would likely require a form of exotic matter with negative energy density to prop the tunnel open against its own intense gravitational forces, which want to collapse it instantly. Whether such matter exists or is even possible remains a topic of fierce debate among physicists. While the mathematics allows for the possibility, turning this theory into a practical reality is far beyond our current understanding. Yet, the mere fact that such a profound idea emerges from our most fundamental equations of gravity keeps it alive as one of the most captivating and awe-inspiring theories about the true nature of black holes. Yet if wormholes offer a speculative exit, our next theory presents a startlingly different fate for a black hole itself, not as a permanent cosmic trap, but as a slowly fading monument. It all began when Stephen Hawking turned his brilliant mind to a seemingly impossible question. What happens when the unchanging rules of gravity meet the fuzzy, unpredictable world of quantum mechanics? His revolutionary answer was Hawking radiation, a theory so profound it fundamentally rewrote our understanding of black holes and their place in the universe. Hawking's genius was to apply quantum theory right at the precipice of a black hole at the event horizon. In the quantum vacuum of space, pairs of virtual particles constantly flicker in and out of existence, borrowing energy from the universe for a fleeting moment before they annihilate each other and vanish, usually without a trace. But Hawking realized that if this particle-antiparticle pair pops into being right at the very edge of an event horizon, something extraordinary can happen. One particle might fall across the point of no return while its partner escapes into space. The particle that falls in has negative energy, and in paying this gravitational debt, it causes the black hole to lose a tiny, almost imperceptible amount of mass. The particle that escapes becomes real radiation, slowly leaking away from the black hole. This is Hawking radiation. The black hole isn't just sitting there, it's subtly glowing, and in the process it's evaporating. This process is achingly slow for any black hole of significant size. A stellar mass black hole would take many times the current age of the universe to evaporate in this way. But for smaller, primordial black holes that might have formed in the intense heat of the Big Bang, this evaporation could be entering its final, dramatic stages right now. As a black hole shrinks, its temperature rises and the rate of evaporation accelerates. The final moments would be a runaway explosion of energy and particles, a final burst of light signaling the end of what was once thought to be an eternal prison. This idea was revolutionary because it created a profound link between three great pillars of physics: gravity, quantum mechanics, and thermodynamics. It suggested that black holes have a temperature and therefore entropy, a measure of disorder. They aren't exceptions to the rules of the universe, they play by them, just in the most extreme environment imaginable. Hawking radiation resolved a thorny paradox by providing a mechanism for information and energy to escape a black hole, though it created a new and even more baffling puzzle: the black hole information paradox. If a black hole evaporates completely, what happens to all the information about the matter it swallowed? Is it truly lost forever, violating a fundamental law of quantum physics? This question remains one of the most heated debates in theoretical physics today, a testament to the enduring power of Hawking's incredible insight. This leads us to a theory that connects two of the universe's greatest enigmas into one. What if the mysterious dark matter that holds galaxies together isn't made of some exotic, undiscovered particle, but is instead composed of black holes? This idea suggests that a vast population of relatively small, ancient black holes, forged in the violence of the Big Bang, could be the invisible mass we've been searching for all along. These aren't the stellar mass black holes formed from collapsing stars or the supermassive giants at galactic centers. These would be primordial black holes, a hypothetical leftover from the universe's first moments. In the incredibly dense and hot conditions just after the Big Bang, random fluctuations in density could have been severe enough for pockets of space to collapse directly into black holes. Unlike their stellar descendants, these primordial black holes could have formed with a wide range of masses, from smaller than an asteroid to many times the mass of our Sun. The theory proposes that a sufficient number of these objects, particularly in a specific mass range, could have been created to account for the dark matter we infer through its gravitational effects. We see galaxies rotating too fast for the visible matter to hold them together. We observe light bending around massive galaxy clusters. Primordial black holes drifting unseen through the cosmos could provide that missing gravitational anchor. But if they're everywhere, why haven't we seen them? The search has focused on constraining possible mass ranges for these hidden objects. For instance, if too many primordial black holes existed with masses similar to a large asteroid, their continuous gravitational lensing effects would have distorted the light from distant supernova in ways we simply don't observe. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, also rule out black holes of a certain size from being the primary component of dark matter, as their accretion would have left a recognizable imprint. These constraints have narrowed the field, but they haven't closed it. A window of possibility remains open for black holes within a specific mass spectrum, particularly those between the mass of a large mountain and that of a gas giant planet, to constitute a significant portion of the dark matter budget. The most exciting prospect for finally detecting these ghostly objects lies not with traditional telescopes, but with a new era of astronomical observation, gravitational wave science. When two primordial black holes in a dark halo slowly inspiral over eons and finally merge, they would send out ripples in space-time gravitational waves, just like the stellar mass black hole mergers already detected by observatories like LIGO and Virgo. In fact, some of the mysterious black hole mergers we've already recorded could potentially be primordial in origin rather than stellar. Future, more sensitive detectors, like the Laser Interferometer Space Antenna LISA, will be able to peer further back in time and listen for the mergers of even older, smaller black holes. Finding a population of merging black holes in the empty voids between galaxies where no stars exist to create them would be a powerful and perhaps definitive piece of evidence that we are finally seeing the dark matter that has eluded us for decades. Yet this slow evaporation of a black hole, this eventual return of energy to the universe, presents us with one of the most profound and troubling puzzles in all of modern physics. It's a puzzle that strikes at the very heart of our understanding of reality, forcing us to choose between two cherished sets of laws that now seem to be at war with one another. This is the black hole information paradox, and it might just have the most violent solution imaginable. To understand the paradox, you first have to understand a fundamental rule of the quantum world: information cannot be destroyed. Information here doesn't mean books or hard drives. It means the complete set of quantum properties that define every single particle in the universe, its mass, its spin, its charge. According to quantum mechanics, that information is forever preserved. If you could somehow reverse all the forces in the universe, you could, in theory, trace every particle back to its origin. You could unscramble an egg. The information about what went into any process must always be present in what comes out. Now consider a black hole. Stephen Hawking showed us that a black hole evaporates by emitting radiation. But this Hawking radiation is random, purely thermal noise. It's like the static from an old radio. It carries no specific information about the material that produced it. If you throw a grand piano, a secret diary, and a mountain of pure hydrogen into a fire, the heat and light that radiate out are featureless. They don't tell you what was burned. Hawking's initial calculations suggested the same was true for black holes. The radiation leaking out appears to have no connection to the specific stars, planets, or spaceships that fell in. When the black hole finally vanishes in a burst of particles, all that unique information about everything it ever consumed seems to have been erased from the universe forever. This conclusion horrified many physicists, as it meant that black holes were violating a cornerstone principle of quantum theory. For decades, physicists wrestled with this. Hawking himself initially believed information was lost, even famously making a bet against fellow physicist John Preskill that he would eventually be proven right. But the tide of opinion began to turn, largely thanks to work by physicist Juan Maldacena exploring a concept called the holographic principle. This mind-bending idea suggests that all the information describing the three-dimensional volume of a black hole might actually be encoded on its two-dimensional surface, the event horizon. If true, the information never actually falls in. It's smeared like a cosmic watermark across the horizon surface. When Hawking radiation is emitted, it could somehow be imprinted with this surface information, preserving it after all. In 2004, Hawking conceded the bet, admitting that information probably does escape. But this resolution created a new and perhaps even more terrifying problem. If information is preserved on the event horizon, then the horizon cannot be the smooth, uneventful space that Einstein's general relativity predicts. For the information to be encoded and then transferred to the outgoing radiation, the event horizon must be a place of immense activity and energy. This line of thinking led to the shocking firewall hypothesis. The theory proposes that the event horizon is not an empty gateway but a searing, chaotic wall of incredibly high energy particles, a literal firewall that would instantly incinerate anything attempting to cross it. Imagine an astronaut foolishly diving toward a black hole. According to Einstein, she would feel nothing special as she crossed the event horizon. It's a point in space that she could only identify in retrospect. But according to the firewall theory, she would never get that far. Instead of a peaceful passage into the unknown, she would collide with a violent curtain of radiation equivalent to the energy of 1 trillion suns the very instant she reached the point of no return. She wouldn't be spaghettified, she would be vaporized. This solution is deeply unsatisfying to many because it simply replaces one paradox with another. General relativity insists that the event horizon must be physically unremarkable for a free-falling observer. The principle of equivalence demands it. The firewall theory shatters this principle, meaning our two most successful theories of physics make completely contradictory predictions about what happens at the edge of a black hole. Either quantum mechanics is wrong and information is lost, or general relativity is wrong and the event horizon is a deadly inferno. This uncomfortable standoff tells us that we are missing a crucial piece of the puzzle, likely a theory of quantum gravity that can unite these two domains and finally reveal what truly happens at the most extreme edge of reality. If we are to take Einstein's equations at their absolute word, they contain not just the blueprint for black holes, but also for their perfect theoretical opposites. These are white holes, and they represent one of the most tantalizing and bizarre symmetries in all of cosmology. The mathematics is clear. Just as a black hole is a region of space from which nothing can escape, a white hole is a region of space that nothing can enter. It is a cosmic fountain, eternally gushing out matter and energy into the universe with unstoppable force, while vehemently rejecting anything trying to fall back in. It's as if you hit rewind on a black hole's life cycle. Instead of a grim endpoint, it becomes a radiant beginning. The concept of white holes emerges naturally from the same solution to Einstein's field equations that predicted black holes, the Schwarzschild solution. This solution is what we call time-symmetric. If you mathematically reverse the direction of time, the equations describing a black hole perfectly transform into the equations describing a white hole. In the pristine world of pure math, the two are flip sides of the same coin. This elegant symmetry is incredibly compelling to theorists, suggesting that if one exists, the other should be possible in nature. But could a white hole actually form? This is where the beautiful mathematics crashes into the messy, irreversible laws of physics as we observe them. A black hole is created through a well-understood, albeit violent, process, the gravitational collapse of a massive star. It's a process that makes thermodynamic sense, moving from order to disorder. A white hole, on the other hand, would have to somehow spontaneously uncollapse. It would need to appear from a singularity already in a state of eruption, blasting matter outward without any prior cause that we can identify within our universe. This seems to violate the second law of thermodynamics, which dictates that entropy or disorder always increases. A white hole would appear to be a process of decreasing entropy, creating order from chaos, which is why most physicists consider them mathematically possible but physically improbable to ever form. This hasn't killed the idea, though. It has simply shifted the speculation to where white holes might exist. One fascinating proposal is that a white hole isn't something that forms on its own, but is rather the distant end of a wormhole. In this scenario, the matter that falls into a black hole in our universe doesn't end at a singularity, but is instead transferred through an Einstein-Rosen bridge and violently expelled out of a white hole in another universe or another distant part of our own. In this view, the black hole and white hole are not separate objects but two connected mouths of a single cosmic tunnel. You enter the black hole here and you are vomited out of the white hole over there. Another, even more speculative idea is that the Big Bang itself could be considered the ultimate white hole, a singular event where the entire universe and all its matter and energy were explosively ejected from a point of infinite density. This draws a compelling parallel. A black hole is a point where our universe ends, and a white hole could be a point where a universe begins. For all we know, our own universe might be the spectacular output from a white hole in a parent cosmos, an idea that turns cosmology into a potentially infinite fractal of births and deaths. The search for observational evidence, however, is the true test. What would a white hole look like in our sky? Astronomers have speculated that certain incredibly violent and brief astronomical events, like some types of gamma-ray bursts, could be potential candidates. Imagine a sudden, inexplicable eruption of energy and particles appearing from a point in space with no remnant left behind. No black hole, no neutron star, just a brilliant one-time flash of creation. If we were to witness such an event that defied all other explanations, the incredible theory of white holes might just transition from a beautiful mathematical curiosity to a revolutionary feature of our physical reality. But that violent firewall and the paradoxical nature of the event horizon lead us to a question that tests the very limits of Einstein's theory. What if the universe's ultimate censor fails? This brings us to a truly radical and controversial concept, the naked singularity. According to the widely accepted cosmic censorship hypothesis proposed by physicist Roger Penrose, every singularity must be decently clothed, hidden from our view forever behind the event horizon of a black hole. This isn't just about modesty, it's a principle that protects the very foundations of general relativity. A hidden singularity keeps its infinite densities and the breakdown of physics a secret, allowing us to predict events outside the horizon with confidence. But what if that hypothesis is wrong? A naked singularity would be a point of infinite density completely exposed to the rest of the universe, with no event horizon to shield us from its unpredictable and lawless core. The formation of such an object would be a cataclysmic event. Imagine a star so tremendously massive and with such a unique, rapid spin that when it collapses at the end of its life, the centrifugal forces are just powerful enough to counteract the inward pull of gravity. Instead of all the matter collapsing smoothly into a single point hidden behind a horizon, the process could become unstable and chaotic. The collapsing matter might rebound, oscillate violently, and ultimately leave behind a bare singularity, a knot of infinite density sitting right out in the open for the entire cosmos to see. The implications of discovering such an object would be simultaneously thrilling and terrifying for physicists. On one hand, it would be the ultimate laboratory for probing the secrets of quantum gravity. We could potentially observe physics operating at energies and densities impossible to recreate anywhere else, offering direct clues to how general relativity and quantum mechanics unite. A naked singularity would be like a crack in the fabric of spacetime, allowing us to peer directly into the heart of the unknown. On the other hand, its existence would mean that the universe is fundamentally unpredictable. The future of any matter or light passing near a naked singularity could not be calculated. Cause and effect would break down at its boundary, making the concept of a deterministic universe impossible. The search for these rogue singularities is already underway, though no confirmed detection has been made. Astronomers look for telltale signs, such as strange patterns of light lensing around a massive but seemingly empty point in space that doesn't behave like a black hole. The light might flicker in unpredictable ways or bend in patterns that defy the smooth warping of a simple massive object. Some theorists have even suggested that certain incredibly powerful and unexplained cosmic explosions could be the birth cries of a naked singularity. Finding one would force us to rewrite our understanding of gravity and accept that the universe contains regions where the known laws of physics simply cease to apply. But what if the monstrous pull of a black hole's singularity isn't the final word? Our journey into the unknown now takes us to a set of theories that dare to reimagine the very nature of these cosmic objects, proposing that what we call a black hole might instead be something even stranger, a black star or a gravistar. These aren't just semantic differences, they are radical alternatives designed to sidestep the terrifying infinities and paradoxes that singularities create, offering a potentially more complete picture of physics at the extreme edge. First, consider the concept of a black star. This idea emerges from loop quantum gravity, a leading contender for a theory of quantum gravity. In this model, the incredible compression of matter at the center of a collapse doesn't proceed all the way to a point of infinite density. Instead, quantum gravity effects produce a tremendous repulsive force, like a cosmic spring that gets compressed to its absolute limit and then pushes back with unimaginable strength. The collapse would halt just short of forming a singularity, leaving behind an ultra-dense ball of matter, a black star. This object would still have an immense gravitational pull, so strong that light would be trapped in tight orbits around it. From a distance, it would look almost indistinguishable from a black hole, dark, massive, and inescapable. But crucially, it would have a surface. There is no point of no return, no event horizon beyond which the laws of physics break down. Matter would still be crushed to incredible densities on this surface, but it wouldn't vanish into a lawless infinity. This single difference solves a host of problems. The black hole information paradox, which hinges on information falling into a singularity and being lost, simply wouldn't exist. Information would never be destroyed. It would just be scrambled on the surface of the black star in an incredibly complex way. The firewall paradox, born from the conflict at the event horizon, also vanishes because there is no event horizon to conflict over. A black star presents a universe that remains predictable and lawful, even under the most extreme conditions. Taking this idea of a surface even further is the truly exotic gravistar, short for gravitational vacuum star. This theoretical object is perhaps one of the most creative solutions ever proposed. A gravistar would be a bizarre bubble in space-time. Its interior would be a void containing a kind of dark energy, similar to the force accelerating the expansion of our universe. This core of negative pressure would exert an outward push, perfectly balancing the inward crush of the gravistar's own immense mass. Surrounding this exotic core would be a shell of incredibly dense, ordinary matter. This shell could be just a few centimeters thick, yet contain the mass of several stars, and that's it. There is no singularity and no true event horizon. The gravitational pull near a gravistar would be almost identical to that of a black hole, but light could still, theoretically, escape from its surface, albeit severely redshifted and weakened. The absence of an event horizon means an astronaut falling toward a gravistar would have a very different experience. Instead of crossing a silent, invisible boundary into oblivion, they would collide with the ultra-dense shell. It would be a catastrophic impact, but it would happen within the known laws of physics. The matter of the astronaut would simply become part of the gravistar's crust. So if these alternatives so elegantly resolve the troubling paradoxes of black holes, why do most astronomers still operate under the traditional model? The challenge, as always, is observation. The differences near the event horizon are subtle and require incredible precision to detect. However, the Event Horizon Telescope, which gave us the first iconic image of the shadow of the black hole in galaxy M87, might one day provide the key. A black hole's shadow is caused by light disappearing across an event horizon. A gravistar or black star with a tangible surface would interact with light in a slightly different way, potentially creating a different kind of shadow or a faint glimmer of light at its center where no light should be. As our imaging technology improves, we may finally get a close enough look to see if the darkness of a black hole is truly absolute, or if it hides a solid surface after all, fundamentally rewriting one of astronomy's most established truths. Yet if the very nature of reality is a projection, what happens when we try to map that reality onto the simplest possible object? This leads us to a principle that uses black holes to make a claim about the entire universe. The holographic principle is arguably one of the most profound and mind-bending ideas to emerge from theoretical physics in the last half-century, and it all started with a deep dive into the entropy of black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole must have entropy. Entropy is a measure of disorder or information content, and Bekenstein realized that when matter falls into a black hole, the information about that matter isn't destroyed, it must be stored somehow. This was a radical notion, as it suggested that a black hole's entropy, and therefore its information content, was proportional not to its volume, but to the surface area of its event horizon. This discovery was a puzzle. In our everyday world, the information needed to describe a system, a room, a star, a person, is proportional to its volume. Think of how much data you'd need to perfectly simulate a glass of water. You'd need to track the position and velocity of every single molecule within that three-dimensional space. But Bekenstein, and later Hawking with his radiation calculations, showed that for a black hole, the maximum amount of information it can contain is dictated by the two-dimensional area of its boundary, not the three-dimensional volume inside. It's as if all the data about everything that ever fell in every atom of every star, every page of every book, is somehow compressed and painted onto the surface of the horizon like a cosmic tattoo. The three-dimensional interior is somehow described by a two-dimensional surface code. This is the essence of the holographic principle, the belief that our perception of a three-dimensional universe might be a projection from a two-dimensional surface at its boundary, much like a hologram where a three-dimensional image is encoded on a flat, two-dimensional piece of film. String theory provides a stunningly successful, concrete example of this principle in action. Through the work of physicists like Juan Maldacena, we have a specific mathematical duality called the AD/CFT correspondence. It demonstrates that a gravitational theory operating in a hypothetical anti-de Sitter space, a kind of bowl-shaped universe, is completely equivalent to a conformal field theory, a quantum theory without gravity, operating on that universe's lower dimensional boundary. In this precise mathematical sense, the entire universe described by the theory is a hologram. The events we perceive happening in the volume of space with gravity are exactly mirrored by events described by quantum particles interacting on the distant boundary. If this is true, then our reality, with its rich depth and dimension, might be a magnificent illusion, a projection from a vast, complex, two-dimensional information field we cannot see. This incredible idea gave birth to a potential solution for our earlier paradoxes, known as black hole complementarity. Proposed by physicists Leonard Susskind and others, this principle is an attempt to resolve the violent conflict between the astronaut's view and the outside observer's view when something falls into a black hole. From the perspective of someone watching from a safe distance, an object falling in never actually crosses the event horizon. Due to the extreme gravitational time dilation, the object appears to slow down, fade, and its information gets smeared and encoded onto the horizon's surface as it radiates away via Hawking radiation. The distant observer sees no loss of information and no violation of quantum laws, but from the astronaut's own perspective, she sails right through the horizon without incident, encountering no firewall, no drama, at least until she meets her fate deeper inside. So, who is right? Black hole complementarity makes the astonishing claim that both views are correct in their own reference frames. The information is both radiated away and it falls into the black hole. This isn't a contradiction because no single observer can ever have both perspectives simultaneously. The laws of physics are complementary. They depend on the observer's viewpoint, much like how light can behave as both a particle and a wave depending on how you measure it. The principle demands that the information is not duplicated, a fundamental quantum rule, but rather that the same information has two different, mutually exclusive descriptions. It's a cosmic sleight of hand that preserves the laws of physics for everyone involved, but at the cost of accepting that reality itself is not absolute but deeply relative. If the holographic principle and complementarity hold true, then black holes are not cosmic dead ends but the ultimate Rosetta Stone, forcing us to decipher the fundamental language of the universe and understand that the richness of our three-dimensional experience might be the most beautiful and complex projection of all. This remarkable view of the universe as a grand projection leads us to a theory that feels like it's lifted straight from science fiction, yet it emerges from the same hard mathematics that gave us black holes. We've seen how they warp space, but what about time? The equations of general relativity tell us that gravity doesn't just bend the fabric of space, it also twists the flow of time itself. And in the specific case of a rotating black hole, this effect could become so extreme that it might open a doorway to the past, creating the theoretical foundation for a time machine. Not all black holes are the simple, static pits in space we often imagine. Those formed from collapsing stars that have no spin are described by the simplest Schwarzschild solution. But most stars rotate, and when they collapse, that spin is conserved, resulting in a much more complex object, a Kerr black hole, named after physicist Roy Kerr, who discovered the solution. A Kerr black hole doesn't have a mere point-like singularity at its center. Instead, its rapid rotation flattens the core into a ring-shaped singularity. This isn't a solid ring of matter, but an infinitely dense, one-dimensional loop where the laws of physics break down. This ring singularity is the key to its strange potential. The intense rotation of the black hole doesn't just affect the singularity. It drags the very fabric of space-time around with it, a phenomenon known as frame dragging. Imagine stirring a cup of tea. The liquid closest to the spoon gets pulled around the fastest. In the same way, space and time near a Kerr black hole are forced into a swirling, whirlpool-like motion. This creates a region outside the event horizon called the ergosphere, where it becomes impossible for any object to remain stationary. Everything is compelled to move in the direction of the spin. Now, here is where the possibility for time travel emerges from the math. Deep within this twisted space-time, the equations allow for the existence of what are called closed time-like curves. A time-like curve is just the path through space-time that any object with mass must follow. In our normal, flat universe, these paths always move forward in time. You can't go back to yesterday. But within the specific, warped geometry around a ring singularity, the path could theoretically curve back on itself, forming a closed loop. An object or person following this path would travel into their own past, eventually returning to the exact same point in space-time from which they began. You would literally meet your former self. The practical challenges of actually using such a phenomenon, however, are so immense they border on the impossible. First, you would have to survive the journey to the region where these closed curves are predicted to exist, which is perilously close to the ring singularity itself. The tidal forces and radiation there would be unimaginably violent. Second, and perhaps more fundamentally, most physicists believe that nature abhors such paradoxes. The mere possibility of a closed time-like curve introduces the infamous grandfather paradox. What if you traveled back in time and prevented your own grandfather from meeting your grandmother, thereby preventing your own birth? How could you then exist to go back in time in the first place? This logical inconsistency suggests that some unknown physical law, perhaps a future theory of quantum gravity, might act to prevent closed time-like curves from forming, making them mathematically possible but physically forbidden. This has led to proposals like the chronology protection conjecture, put forward by Stephen Hawking, which essentially suggests the universe has a built-in mechanism that prevents time travel to the past in order to preserve causality and make history consistent. The universe might simply not allow a situation where you could change an event that has already happened. While the Kerr solution allows for the potential of time travel, most physicists view it as a fascinating mathematical quirk rather than a practical blueprint, a sign that our current theory of gravity, while incredibly powerful, is still incomplete when pushed to its absolute limits. Yet for all the mind-bending brilliance of the holographic principle, it remains a highly abstract solution to the information paradox. What if the answer isn't a cosmic projection, but something far more tangible, etched directly into the fabric of the black hole itself? This brings us to a fascinating and more recent development known as the quantum Hare theorem, an idea that suggests black holes might not be the perfectly smooth, featureless objects we once thought, but could instead possess subtle, distinguishing characteristics that preserve a memory of everything they've ever consumed. The traditional view, based on work by physicists like Israel, Carter, and Robinson, resulted in the famous no-Hare theorem. This theorem states that an isolated black hole can be completely described by just three quantities: its mass, its electric charge, and its angular momentum or spin. Everything else, whether it formed from a star made of hydrogen or one made of iron, whether you threw in a grand piano or a library of books, is irretrievably lost behind the event horizon. The black hole has no hair, no unique features or styling that betray its history. It is the ultimate cosmic minimalist. The information paradox, of course, tells us this smooth, featureless picture can't be the full story. The quantum Hare theorem, developed by Professors Xavier Comet and Stephen Hsu, challenges the no-Hare idea at a fundamental level. They propose that when you apply the rules of quantum mechanics to the immensely strong gravitational field of a black hole, a new type of distinguishing feature emerges. This isn't hair in the visual sense, it's a set of infinitesimally subtle differences in the gravitational field itself, imprinted at the moment of a particle's descent. Here's how it might work. Imagine an electron with a specific quantum property, like its electromagnetic charge, falling into a black hole. According to classical physics, that charge just adds to the total charge of the black hole, and the specific details of that electron are gone. But quantum mechanics introduces an intimate connection between particles and the fields they produce. The theory suggests that as the electron falls in, its unique quantum information doesn't vanish. Instead, it leaves a tiny, permanent imprint on the gravitational field of the black hole, like a fingerprint pressed into soft clay. This imprint is the quantum hair. It's a way for the information about what fell in to be preserved not inside the black hole, but in the way its gravity interacts with the rest of the universe. The mechanism for this relies on a quantum phenomenon known as vacuum polarization. Even in empty space, the quantum vacuum is a seething sea of virtual particles popping in and out of existence. The immense gravity of a black hole polarizes this vacuum, effectively organizing these fleeting particles. When a real particle falls in, it disturbs this organized vacuum in a unique way, and that disturbance gets locked into the fabric of space-time surrounding the black hole. The information is saved not on a two-dimensional holographic surface, but in the complex, quantum-structured gravitational field that permeates the space around the horizon. If this theory holds, it would be a monumental step toward resolving the information paradox without the need for firewalls or violations of fundamental principles. The information never actually disappears, it's just translated into an incredibly complex gravitational code. Hawking radiation, then, wouldn't be random thermal noise. As the black hole evaporates, this quantum hair would subtly influence the particles that are emitted, ensuring the outgoing radiation carries the signature of everything that ever fell in. The information is gradually and faithfully returned to the universe. Of course, detecting such an effect is a staggering challenge. The differences in the gravitational field would be unimaginably small, likely on the Planck scale, far beyond our current ability to measure. However, the mere mathematical possibility offers a new and compelling direction for theoretical physics. It suggests that black holes are not the simple, destructive endpoints we once imagined, but potentially the most sophisticated and complex information processing systems in the cosmos. Their histories written in a language of gravity and quantum fields that we are only just beginning to learn how to read. These cosmic collisions between the most extreme objects in the universe lead us to a theory that sounds like the plot of a spectacular science fiction movie, but is grounded in very real astrophysical possibility. We've explored black holes and neutron stars as separate entities, but what happens when these titans meet? The result could be a bizarre and fleeting hybrid object, a cosmic chimera that defies simple categorization and offers a unique window into the behavior of matter at the most extreme densities imaginable. A neutron star is already a stellar corpse pushed to its absolute limit. Born from the supernova explosion of a massive star, it's an object so dense that the protons and electrons in its atoms have been forced together to form neutrons. A sugar cube-sized piece of neutron star material would weigh as much as a mountain here on Earth, but even this incredible density has a limit. There's a theoretical maximum mass that a neutron star can support against its own gravity before it undergoes a complete gravitational collapse into a black hole. This threshold is known as the Tolman-Oppenheimer-Volkoff limit, and it's a frontier where matter's final stand against gravity ultimately fails. Now, imagine a binary system where a neutron star is locked in a fatal dance with a black hole companion. Over millions of years, their orbits decay as they lose energy by emitting gravitational waves. They spiral closer and closer until the black hole's immense tidal forces begin to strip material away from the neutron star's surface. This is the moment of creation for a potential hybrid. The neutron star isn't simply swallowed whole, it's shredded. A tremendous tidal tail of super-dense neutron-rich matter is pulled from the star, wrapping around the black hole in a furious, ultra-hot accretion disk. For a brief, glorious moment, the system is no longer just a black hole and a neutron star. It becomes a single, chaotic entity, a black hole surrounded by a torus of material that is essentially the guts of a neutron star, a substance with properties we can only theorize about in laboratories. The fate of this material depends on the masses of the two objects. If the black hole is relatively small and has a high spin, the neutron star matter might form a stable, long-lived disk that could power some of the most energetic explosions in the universe. But if the black hole is too massive, it simply gulps down the entire neutron star in one quick bite, leaving little trace behind. It's in that middle ground, the tidal disruption scenario, where the most interesting physics happens. The pressures and densities within that swirling maelstrom of neutron star debris could be so extraordinarily high that they trigger a phase transition, transforming the neutrons into their constituent parts, a soup of free quarks and gluons, creating what is known as a quark star or a strange star if strange quarks become involved. This hypothetical quark matter could be the true ground state of matter, even more stable than the atomic nuclei we're made of. For a few milliseconds, the black hole might be wearing a crown not of neutron matter, but of pure quark-gluon plasma, a state of matter that hasn't existed freely since the first microseconds after the Big Bang. This hybrid object, a black hole enshrouded by a quark matter accretion disk, would be one of the most exotic and short-lived phenomena in the cosmos. It would then rapidly feed this unique material into the black hole, a final sacrifice before the system settles down into a quiet, slightly more massive black hole. The key to discovering these events lies not with light telescopes, but with the ripples they send through space-time itself. The gravitational wave signal from such a merger has a very specific and telltale signature that differs from two black holes or two neutron stars colliding. The initial in-spiral would sound similar to other binary mergers, but the moment of collision would be dramatically different. Instead of a clean chirp followed by a ring down as two black holes merge, the signal would be messier, more complex. The tidal disruption of the neutron star would imprint itself on the gravitational waves, adding a high-frequency scream to the signal as the star is stretched and torn apart. Furthermore, the eventual collapse of the resultant hypermassive neutron star or quark matter disk into the black hole would produce its own unique ring-down signature. By meticulously analyzing the gravitational wave data collected by observatories like LIGO, Virgo, and the Future Laser Interferometer Space Antenna or LISA, scientists can hunt for these subtle deviations in the signal. Finding them would not only confirm the existence of these incredible hybrid objects, but would also provide unparalleled data on the equation of state of neutron star matter, essentially telling us how this super-dense material behaves under the most extreme conditions, and potentially providing the first direct evidence for the existence of stable quark matter. Each such collision is a natural universe-scale experiment, giving us a front-row seat to physics that we could never hope to recreate on Earth. This astonishing transformation of matter into the most exotic states imaginable shows the incredible power of black holes to reshape their surroundings. But what if their influence isn't confined to their immediate vicinity? What if the very largest black holes are shaping the destiny of the entire cosmos? This brings us to a theory that connects the most enigmatic objects in the universe to its most mysterious force, proposing that supermassive black holes might be the hidden engines behind dark energy and the accelerating expansion of the universe. For decades, astronomers have known that the universe isn't just expanding, that expansion is speeding up. Something is counteracting the relentless pull of gravity on cosmic scales, pushing galaxies apart faster and faster. We call the source of this repulsive force dark energy, but its fundamental nature remains one of the biggest unsolved puzzles in physics. The leading candidate is the cosmological constant, a property of the vacuum of space itself that exerts a negative pressure. But why this energy has the specific value it does is a complete mystery. Now, a radical new idea suggests the answer might not be found in the empty vacuum, but at the hearts of galaxies within their supermassive black holes. The theory, sometimes called the cosmological coupling model, proposes a direct and profound link between the growth of these black holes and the expansion of the universe itself. Think of it this way: as the universe expands, the space between galaxies grows. According to this idea, the supermassive black holes sitting at the centers of those galaxies are not isolated from this process. They are cosmologically coupled. Their internal properties, specifically their vacuum energy, are somehow tied to the overall expansion rate of the cosmos. As the universe grows, the energy contained within these black holes grows with it. This isn't about the black holes accreting more gas and stars. This is a more fundamental connection. The proposal is that the dark energy we measure across the universe might actually be an emergent property, the collective result of the vacuum energy stored inside every supermassive black hole. In this view, these black holes aren't just inhabitants of the universe, they are active participants in driving its large-scale evolution. Their cumulative gravitational influence, now coupled with this evolving internal energy, could provide the persistent push that accelerates the expansion. How could this possibly work? The mathematics points towards the black hole's interior. Remember, we don't know what happens inside an event horizon. Our best theories suggest it could contain a singularity, or perhaps something else entirely, like a region of extremely high vacuum energy. If that interior vacuum energy is linked to the global expansion of space, then as the universe gets bigger, the energy inside the black hole increases, and so does its mass. The black hole gains mass not by eating matter, but simply because the universe is expanding. This growing mass then contributes even more to the overall curvature of spacetime, creating a feedback loop that fuels the acceleration. The implications of this are staggering. It would mean that dark energy isn't a smooth, uniform field permeating empty space, but is instead concentrated at discrete points, the centers of galaxies. The accelerated expansion of the universe wouldn't be a passive background process. It would be an active phenomenon driven by the most massive objects in existence. This theory also offers a potential solution to the cosmic coincidence problem, the puzzling observation that we live in the brief epoch of the universe's history where the density of matter and dark energy are roughly comparable. If dark energy is tied to black holes, its influence has grown as black holes have grown over cosmic time, naturally explaining why it only began to dominate the universe's evolution relatively recently. Of course, this is a highly speculative and controversial idea, and the scientific community is actively looking for ways to test it. The key prediction is that the masses of supermassive black holes should be larger in the modern universe than they were in the past, and that this growth should be correlated with the expansion history of the cosmos, not just with the availability of gas and stars to consume. By carefully measuring the masses of black holes in distant galaxies, which also means looking back in time, astronomers hope to see this mysterious growth in action. If the data shows that black holes were more massive than expected billions of years ago, it could be the first crucial evidence that we are indeed seeing the cosmic engines of dark energy at work, forever linking the fate of the largest black holes to the ultimate destiny of the universe itself. But to truly escape the paradox of the singularity, we must venture beyond Einstein's theory and into the speculative realm of quantum gravity. This brings us to a theory that offers a stunning alternative to the grim endpoint of infinite density, the Planck star. Imagine the final collapse of a massive star. According to general relativity, it's a one-way trip to a singularity. But if we apply the principles of loop quantum gravity, a leading candidate for uniting relativity and quantum mechanics, the story changes dramatically. Instead of collapsing to zero size, the stellar core reaches a point of maximum possible density, a density so immense it is defined by the fundamental constants of nature, the Planck density. At this critical threshold, quantum gravity effects become overwhelmingly powerful, acting not as a crushing force but as a tremendous repulsive pressure. It's as if the collapsing matter hits a quantum spring. The implosion halts, reverses, and the core undergoes a violent bounce, exploding outward. This reborn, ultra-dense object is a Planck star. A Planck star wouldn't be a star in the traditional sense, fusing elements in its core. It would be a ball of matter existing for only a blink of an eye, but its properties are mind-boggling. Because it is so incredibly small and dense, its gravitational pull remains immense. to a distant observer, it would still be hidden behind what appears to be an event horizon. The bounce happens deep inside this region, completely invisible from the outside. The black hole, from an external viewpoint, would seem perfectly ordinary for most of its life. The dramatic difference would only become apparent in the far, far future when the black hole evaporates via Hawking radiation. As the black hole shrinks over eons, the event horizon would slowly recede inward. After an almost unimaginable amount of time, the horizon would shrink enough to reveal the Planck star hiding within, which would then explosively release all the matter and energy it contained at the moment of its bounce. The final stage of black hole evaporation wouldn't be a quiet fizzle, but a spectacular, delayed supernova. This concept of a bounce leads to an even more astonishing possibility, that the rebound inside a black hole could be the birth of an entirely new universe. This is the black hole cosmology theory, and it turns the idea of a black hole as a cosmic dead end on its head, transforming it into a cosmic nursery. The proposal is that the quantum bounce that creates a Planck star is so violent and expansive that it initiates a new period of inflation, a rapid, exponential stretching of spacetime. However, this new spacetime is causally disconnected from our own. It forms its own separate bubble universe with its own physical constants and laws of physics. In this breathtaking scenario, every black hole in our universe could be a Big Bang event for a child universe. Our own cosmos might itself have been born this way from a black hole in a parent universe. This creates a fractal, multiverse model of reality, where universes beget other universes through their black holes, an endless cycle of cosmic death and rebirth. The evidence for such a theory is understandably elusive. We cannot peer inside a black hole to watch a Planck star form. However, if a child universe were to be born from a black hole in our cosmos, some theorists suggest the moment of its birth might leave a faint imprint on the cosmic microwave background radiation, the afterglow of our own Big Bang. We could, in principle, search for anomalous patterns or circles in this radiation that might be the scars of such a primordial event. Furthermore, the final explosion of an old, evaporating black hole revealing its Planck star core would be a unique astrophysical signal. We would look for a sudden, incredibly energetic burst of radiation with no other possible explanation, a signature of a universe paying back a debt of matter and energy it borrowed trillions of years ago. While these ideas push the boundaries of observation, they demonstrate how replacing the singularity with a quantum bounce doesn't just solve a mathematical problem. It opens a door to a vastly richer and more connected multiverse where black holes are not tombs but the wombs of new realities. This profound link between gravity and thermodynamics leads us to a theory that fundamentally reshaped our understanding of both information and the universe's most enigmatic objects. It all started when a young graduate student named Jacob Bekenstein made a daring and, at the time, seemingly heretical proposal. He suggested that black holes must have entropy. To grasp why this was so revolutionary, we need to understand what entropy represents. In the broadest sense, entropy is a measure of disorder, but more precisely, it's a measure of the number of microscopic states that correspond to a single macroscopic state. It's the hidden information content of a system. A cold, neat ice cube has low entropy. A puddle of warm water has higher entropy. Bekenstein's radical insight was that when matter carrying entropy falls into a black hole, that entropy doesn't just vanish. It must be accounted for, or else the second law of thermodynamics, which states that the total entropy of the universe always increases, would be violated every time something disappeared behind an event horizon. Bekenstein proposed that a black hole's entropy is not proportional to its volume, as it is for any other object we know, but to the surface area of its event horizon. The formula is stunning in its simplicity and profundity. The entropy of a black hole is equal to the area of its event horizon divided by 4 times a fundamental constant of nature. This means the maximum amount of information a black hole can contain is determined by its surface area, not the volume of space it encloses. Think of how bizarre this is. To describe the contents of your house, you would need information about every item within its three-dimensional space. But to describe the contents of a black hole, according to this principle, you would only need a two-dimensional map painted on its outer surface. This was the first strong hint of the holographic principle, the idea that our perception of a three-dimensional reality might be a projection from a two-dimensional surface. This idea, now known as the Bekenstein bound, places a fundamental limit on the amount of information that can be contained within any finite region of space. It states that the maximum entropy, and therefore the maximum information that can be stored in any volume of space, is directly proportional to the surface area surrounding that volume, not the volume itself. Your laptop, your brain, the entire observable universe, all are ultimately constrained by this cosmic data limit. This transforms our view of reality. The universe isn't like an infinite hard drive. It's more like a projector with the true, complex information existing on a boundary surface. A black hole, with its immense gravity, simply saturates this limit, operating at the maximum possible entropy for its size. It is the ultimate information storage device, the cosmic equivalent of a fully formatted hard drive. The implications of this discovery ripple through all of physics. It forged an unbreakable link between information theory, thermodynamics, and gravity, three fields that were previously thought to be largely separate. It provided the crucial hint that led Stephen Hawking to his discovery of radiation, as he set out to prove Bekenstein wrong about black holes having temperature, and instead found himself confirming the young physicist's brilliant intuition. Most importantly, the Bekenstein bound suggests that information is a physical substance as fundamental as matter and energy. It cannot be created or destroyed, it can only be transformed. When something falls into a black hole, its information isn't lost. It is somehow encoded onto the event horizon, scrambled into a form we don't yet understand, but preserved nonetheless. This insight is the bedrock upon which all modern solutions to the information paradox are built, pointing toward a deeper, holographic truth about the nature of our universe. If the information within a black hole is so exquisitely preserved and encoded on its boundary, what is it actually doing in there? This leads us to a theory that reimagines these cosmic giants not as inert tombs, but as the most powerful processing engines in the natural world. The idea that a black hole could be a quantum computer is not just a metaphor. It emerges directly from the holographic principle and the work on black hole entropy. Just as a quantum computer uses the bizarre rules of quantum mechanics to perform calculations at incredible speeds, a black hole might be using the fundamental laws of physics to process information on a cosmological scale. Think about what a quantum computer does. It leverages quantum bits or qubits, which can be in a state of 0, 1, or both at the same time, a phenomenon called superposition. This allows it to explore a vast number of possibilities simultaneously, solving certain problems exponentially faster than any classical computer could. Now consider the event horizon of a black hole. According to the holographic principle, all the information about what fell in is stored on this two-dimensional surface. The individual Planck-sized pixels that make up this surface, each one holding a single bit of information, could be thought of as the ultimate qubits. They aren't just static bits. The intense gravitational and quantum environment would keep these bits in a constant, dynamic state of flux and interaction. The black hole isn't just a hard drive, it's a processor. It's continuously performing operations on this information, scrambling it according to the laws of physics in an unimaginably complex computation. The efficiency of this process is what is so astounding. Seth Lloyd, a pioneer in quantum computing, calculated the computational capacity of the universe. He then looked at a black hole and found that it saturates the ultimate physical limits of computation. A 1-kilogram black hole, a tiny, hypothetical object, could perform around 10 to the 51 operations per second on some 10 to the 16 bits. But a stellar mass black hole operates on an entirely different level. Its computational power is tied to its entropy, which is enormous. For the entire lifetime of the black hole, until it evaporates away, it is performing an astronomical number of logical operations on the information it contains. It is, by definition, the most efficient information processor allowed by the laws of physics. Nothing in the universe can compute more operations per second per unit of energy than a black hole. This isn't computation with a purpose or a designed output like solving a math problem. It's more fundamental. The black hole is simply executing the laws of physics. The act of information falling in, becoming encoded on the horizon, interacting with other bits, and eventually being radiated away as Hawking radiation is the computation. The input is the initial state of the infalling matter. The processing is the complex scrambling and unitary evolution dictated by quantum mechanics. The output is the subtle, information-laden Hawking radiation. In this view, the entire life cycle of a black hole is one incredibly long, incredibly complex calculation. It's taking the ordered information of a star and transforming it into what looks like disordered thermal radiation, but in a way that perfectly preserves the underlying quantum information through the process. What could this possibly mean for our understanding of the cosmos? It suggests that the universe might not just contain computers. It might be a computer, or more precisely, a network of computational processes. The most extreme objects within it are simply the most powerful nodes in this cosmic network. If black holes are the ultimate quantum computers, then they set the physical limits for information processing. Any technology we could ever build, no matter how advanced, would be constrained by the same fundamental thermodynamic and quantum limits that a black hole already operates at. They represent the final frontier of what is computationally possible. This perspective also offers a fascinating new angle on the information paradox. The paradox arises from thinking that information is lost inside the black hole. But if the black hole is a quantum computer, then information isn't lost, it's being processed. The problem of retrieving the information from the Hawking radiation is analogous to the challenge of looking at the output of a massive calculation and trying to reverse engineer the initial input data. It seems random and noisy, but if you perfectly understand the algorithm that was run, in this case the precise laws of quantum gravity, you could, in theory, reverse the computation and recover the original information. The black hole isn't deleting data, it's running a program so complex that we simply don't know the code yet. Understanding that code wouldn't just solve a paradox, it would reveal the deepest computational language of the universe itself. Yet if the universe is fundamentally a computation, as the quantum computer theory suggests, then the event horizon of a black hole is where we should be able to listen in on the processing itself. This brings us to a fascinating and contentious proposal that has emerged directly from the era of gravitational wave astronomy, the search for gravitational wave echoes. The idea is stunning in its simplicity. When LIGO and Virgo detect the signal of two black holes merging, they record a very specific pattern: the rapid chirp of the inspiral as the black holes race toward each other, followed by the ring down, a fading series of vibrations as the new, larger black hole settles into a stable state. According to Einstein's general relativity, that should be the end of the story. The event horizon is a one-way street, and the ring-down signal should decay smoothly into silence. But what if that silence is punctuated by something more? The echo hypothesis proposes that if the event horizon is not the perfect, smooth barrier that classical physics describes, If it has some kind of quantum structure or is replaced by a physical surface like that of a gravistar or a firewall, then the gravitational waves produced in the merger won't just vanish. Instead, a tiny fraction of them could bounce off this exotic structure lurking just where the event horizon should be. These reflected waves would travel back into the black hole's interior, only to bounce again and perhaps again, each time leaking out a little bit of energy. To a distant observer, this would manifest as a series of faint, repeating aftershocks following the main ring-down signal, a faint, decaying echo of the original cataclysm. Finding such an echo would be nothing short of revolutionary. It would be the first direct observational evidence that there is something beyond the classical picture of a black hole, a microscopic structure at its edge that modifies the perfect emptiness of the event horizon. Different theories predict different echoes. A firewall of high-energy particles would create one kind of echo signature. The hard surface of a gravistar or black star would produce another. The specific timing and amplitude of these repeating signals would act like a sonar scan, allowing us to literally probe the quantum geometry of the most extreme environment in the universe. We wouldn't just be inferring the existence of quantum gravity, we'd be listening to its vibrations. The search for these echoes has been underway almost since the first gravitational wave detection was announced. Several research groups have reanalyzed the public data from LIGO and Virgo, applying sophisticated signal processing techniques to look for these faint, repeating patterns in the noise following the main event. Some early analyses reported tentative evidence for echoes in a number of events, sending ripples of excitement through the theoretical physics community. The statistical significance of these claims, however, has been the subject of intense and ongoing debate. Other teams, using different data analysis methods or noise models, have found no such evidence, attributing the initial signals to random noise fluctuations or subtle instrumental artifacts that can mimic an echo. The challenge is immense. The predicted echo signal is incredibly weak, buried deep within the noisy data of detectors that are already operating at the very limits of human engineering. Distinguishing a true astrophysical echo from the complex background is a monumental task. Furthermore, the theoretical predictions themselves are still being refined. The precise nature of the echo depends critically on the exact quantum properties of the proposed surface, which are not yet fully understood. This means scientists are looking for a signal whose precise shape is still somewhat uncertain, making it even harder to confirm a detection beyond a reasonable doubt. Despite these challenges, the hunt continues, driven by the profound implications of a potential discovery. Future upgrades to LIGO, Virgo, and the upcoming laser interferometer space antenna will provide far cleaner and more sensitive data, offering a much better chance to either confirm or definitively rule out the existence of these echoes. Whether they are found or not, the very act of looking forces us to ask deeper questions about the nature of black holes. The echo hypothesis represents a beautiful synergy between theory and observation, where a seemingly abstract debate about firewalls and quantum structure has been translated into a concrete, testable prediction that we can go out and search for with our instruments. It transforms a philosophical puzzle into an experimental one, pushing our understanding of reality to the very brink. But what if a black hole's life isn't a simple story of growth and evaporation? What if, under the right conditions, it can undergo a radical transformation as fundamental as water freezing into ice? This leads us to a theory that sees black holes not as static objects, but as dynamic entities capable of their own kind of metamorphosis. The concept of black hole phase transitions emerges from the powerful link between gravity and thermodynamics, suggesting that under certain conditions, a black hole can spontaneously and dramatically shift its entire state, revealing new properties as exotic as any state of matter we know. To understand this, we need to think of a black hole not just as a gravitational pit, but as a thermodynamic system with its own temperature and entropy. Just like water can exist as a liquid, solid, or gas depending on its temperature and pressure, a black hole's behavior is governed by its mass, charge, and spin. In the 1970s, physicists like David Robinson and Stephen Hawking established a set of laws for black hole mechanics that perfectly mirror the classical laws of thermodynamics. This wasn't just a cute analogy, it was a profound insight that these cosmic objects are genuine thermal systems. The most fascinating phase transition for a black hole is akin to the boiling point of water. Imagine a very small, very hot black hole. It's evaporating rapidly due to Hawking radiation, losing mass and getting even hotter in a runaway process. Now place this black hole in a perfectly enclosed box filled with thermal radiation, a concept known as the canonical ensemble in thermodynamics. As the black hole evaporates, it feeds energy into the box, heating up the radiation bath. There comes a critical point where the system must find a new equilibrium. The theory suggests that the black hole can undergo a first-order phase transition. In one possible scenario, the small, hot black hole becomes unstable and rapidly boils away, transferring all of its energy and entropy to the radiation in the box. In another, more stable configuration, a large, cold black hole could form, one that is in a balanced, equilibrium state with the radiation surrounding it. It's as if a steaming puddle instantly and violently transformed into a massive, tranquil iceberg. The mathematics behind this points to something even more spectacular: the potential for black holes to have multiple, distinct states of existence, much like how water can become a supercritical fluid under extreme heat and pressure. For a charged black hole, known as a Reissner-Nordström black hole, the equations reveal a thermodynamic behavior strikingly similar to that of a van der Waals fluid, the model used to describe the liquid-gas phase transition. This black hole can have a first-order phase transition line that ends at a critical point. Beyond this critical point, the sharp distinction between a small black hole phase and a large black hole phase vanishes. They merge into a single, new, supercritical black hole state, a unique phase of gravitational existence with its own unknown properties. These aren't just abstract mathematical curiosities. They could have profound implications for the stability of the universe itself and the fabric of spacetime. Some models in string theory suggest that the vacuum of space we inhabit might not be the true, most stable state of the universe. It could be a false vacuum, metastable and poised to decay into a lower energy state. In this scenario, a black hole could act as a nucleation site for this catastrophic phase transition. The immense curvature of spacetime near a black hole could provide the seed around which a bubble of true vacuum spontaneously forms. This bubble would then expand outward at the speed of light, rewriting the fundamental constants of nature, like the strength of forces or the mass of electrons, in its wake. Anything caught in this wave would cease to exist as we know it. Thankfully, the probability of this happening in our universe is considered vanishingly small. But the mere possibility highlights how black hole phase transitions aren't isolated events. They could be intimately tied to the ultimate fate of all reality. The search for evidence of these transitions pushes the limits of observation. We can't put a black hole in a laboratory box. However, astronomers might look for indirect signatures. If a population of small, primordial black holes from the early universe underwent such a phase transition, it might have left a specific imprint on the cosmic microwave background or generated a unique background of gravitational waves that future observatories could detect. Furthermore, by meticulously studying the populations and properties of black holes across the cosmos, we might find statistical evidence for these different phases, much like a geologist identifying different mineral phases under pressure. Each phase transition represents a black hole unlocking a new chapter in its life, a dramatic metamorphosis hidden within the elegant equations of gravity and thermodynamics. While our solar system feels like a well-mapped neighborhood, astronomers have been tracking a persistent anomaly in its farthest suburbs, a gravitational whisper hinting at something massive lurking in the frozen darkness beyond Neptune. This mystery is known as Planet 9, a hypothetical world thought to be several times more massive than Earth, shepherding a collection of small, icy objects into strangely clustered orbits. But what if this hidden perturbator isn't a planet at all? One of the most provocative theories suggests we are not being circled by a rogue world, but by a primordial black hole. This idea reimagines the hypothetical Planet 9 not as a ball of rock and ice, but as a captured relic from the universe's explosive beginning. A primordial black hole with a mass roughly 5 to 10 times that of Earth would exert the exact same gravitational pull on the distant Kuiper belt as a planetary body. From a gravitational perspective, the two are effectively identical. This makes the theory both compelling and incredibly difficult to disprove, forcing us to consider detection methods that go far beyond simply pointing a telescope into the night sky. So how could we possibly find a black hole that is, by its very nature, invisible? Astronomers have proposed two ingenious hunting strategies. The first involves looking for the telltale flashes of radiation that would betray its presence. As a primordial black hole drifts through the outer solar system, it would occasionally pass through dense clouds of interstellar gas or the sparse dust of the Oort cloud. Even in these near-perfect vacuums, the immense gravity would pull matter in, accelerating it to incredible speeds. As this material compresses and heats up in a process called accretion, it would emit a faint but detectable stream of radiation, primarily in the form of gamma rays and X-rays. We wouldn't see the black hole itself, but we could see the glow of its last meal. Sensitive all-sky survey instruments, like those on the Fermi Gamma Ray Space Telescope, could potentially pick up these telltale, moving pinpricks of high-energy light, tracing the path of an object that emits no light of its own. The second method relies on an even more futuristic form of astronomy, gravitational wave detection. If this object is indeed a black hole, it may not be alone. It could be part of a binary system, locked in a dance with a companion object, perhaps another small black hole or a dense, captured asteroid. As these two objects orbit each other, they would ripple space-time, emitting a continuous, faint stream of gravitational waves. While these waves would be too low frequency for current ground-based detectors like LIGO to hear, the next generation of space-based observatories, such as the Laser Interferometer Space Antenna, will be tuned to precisely this frequency range. LISA could essentially listen for the humming of a binary system orbiting in our solar system's backyard, a clear auditory signature that no planetary object could ever produce. The implications of finding such an object would be staggering, offering a scientific bonanza. A nearby primordial black hole would provide an unparalleled natural laboratory for testing the laws of physics. We could study Hawking radiation up close, probe the nature of dark matter if these objects are indeed its constituents, and even contemplate future missions to study it, pushing the boundaries of exploration from planetary science to direct astrophysical inquiry. It would transform our understanding of the solar system's inventory, proving that our cosmic backyard contains not just planets and asteroids, but also the most exotic objects born from the universe's first moment. The hunt for Planet 9 has always been a search for a missing world, but it might ultimately lead us to the discovery of something infinitely more mysterious and profound. But just as we ponder the potential for a black hole hiding in our own solar system, we are forced to shrink our imagination down to an almost incomprehensible scale, to a realm where the cosmic and the quantum violently collide. This brings us to a theory that sounds like it was ripped from the pages of a particle physicist's wildest dream journal, the concept of black hole atoms. Imagine taking the smallest, most fundamental building block of matter, an atom, with its nucleus and orbiting electrons, and replacing the proton at its heart with something infinitely more bizarre, a microscopic black hole. The result would be a black hole atom, a stable, quantum-bound system where an electron orbits a singularity, a place where the rules of the atomic world meet the warped physics of gravity's ultimate manifestation. The very possibility of such an exotic atom hinges on the existence of small black holes, specifically those with a mass low enough that their gravitational pull on an electron could be comparable to the electromagnetic force of a proton. We're talking about black holes lighter than a mountain, perhaps even as small as an asteroid. For a black hole to have a similar gravitational influence on an electron as a proton does via electromagnetism, its mass would need to be around the Planck mass, which is a minuscule 20 micrograms. An electron orbiting this tiny, massive object would form a stable, hydrogen-like atom, but with a nucleus that isn't a composite particle made of quarks, but a fundamental knot of pure spacetime curvature. The behavior of this system would be a fascinating hybrid of known physics and utter speculation. In many ways, it would behave like a regular atom. The electron would occupy quantized energy levels, absorbing and emitting photons as it jumped between orbitals. From a distance, a cloud of black hole hydrogen might look almost identical to a cloud of regular hydrogen gas. But the devil, as always, is in the details, or in this case, in the nucleus. The intense, point-like gravity of the microscopic black hole would cause subtle deviations in the electron's energy levels, a unique fingerprint that a sensitive enough spectrometer could potentially detect. Furthermore, this isn't a stable partnership forever. The black hole nucleus would itself be evaporating via Hawking radiation. For a black hole atom to last longer than a fleeting instant, the black hole's mass must be large enough that its evaporation timescale is longer than the age of the universe. Otherwise, the entire atom would vanish in a flash of radiation the moment it formed. How could such a bizarre entity ever come into existence? They are almost certainly not forming naturally in the universe today. The conditions required to create a microscopic black hole are unimaginably extreme, far beyond the pressures found in the core of any star or the collision of any two asteroids. The only place we can conceive of their creation is in the high-energy collisions of particle accelerators, under a very specific and still theoretical circumstance. If our universe has extra spatial dimensions as predicted by some string theory models, then the fundamental scale of gravity could be much, much lower than we observe. In such a scenario, the Large Hadron Collider might be able to concentrate enough energy into a small enough volume to literally punch a hole in spacetime, creating a micro-black hole in a shower of particles. This fleeting singularity would then rapidly snatch up an electron from the surrounding chaos, potentially forming a black hole atom for a fraction of a second before it decayed. Detecting such an event would be the discovery of the millennium, and physicists have thought carefully about what to look for. It wouldn't be a simple splash in a detector. The signature would be a very specific and strange sequence of events. First, the collision would produce the Hawking radiation signature of a decaying micro-black hole, a spray of particles and radiation with a characteristic thermal spectrum. But nestled within that signal, analysts would search for the telltale signs of electron energy transitions, the specific frequencies of light that would be emitted as an electron settled into orbit around the newly formed singularity before both of them evaporated away into nothingness. It would be like seeing the brief, brilliant flash of an atom being born and dying all at once, a quantum sigh in the data. The existence of black hole atoms would fundamentally change our understanding of the boundaries between physics disciplines. It would prove that gravity and quantum mechanics aren't just compatible at these extreme scales. They can cooperate to form stable, composite structures. It would open up an entirely new field of study, quantum gravitational chemistry, where we could explore the periodic table of elements that have singularities for nuclei. While the chances of creating or finding one are incredibly slim, the mere fact that the equations allow for such a possibility forces us to expand our view of what matter can be, revealing a universe far stranger and more wonderful than we ever thought possible. This astonishing notion of quantum scale structures brings us to perhaps the most expansive and humbling theory of all, the idea that every black hole might be an entire universe in its own right, and that our own cosmos could simply be the interior of a black hole residing within a far grander parent universe. This isn't just a poetic metaphor, it's a serious cosmological model that emerges from the mathematics of general relativity and offers a breathtaking vision of a potentially infinite fractal multiverse. The seed of this idea is found in the behavior of matter at the moment of a black hole's formation. When a massive star collapses, it falls inward toward a singularity, a point of infinite density where our known laws of physics cease to function. But what if that collapse doesn't end at a singularity? Some interpretations of the equations, particularly when quantum gravity effects are considered, suggest that the incredible inward rush of space and matter could rebound. This is the concept of a quantum bounce, where the collapse reverses into an expansion. The immense energy and density present at the moment of the bounce would be more than enough to trigger a new period of rapid inflation, an exponential stretching of spacetime. However, this new, expanding spacetime would be causally disconnected from our own. It would form its own separate bubble universe with its own physical constants and potentially its own unique laws of physics. In this stunning scenario, the interior of every black hole becomes the birthplace of a new cosmos. This leads to a cyclic model of cosmology that stands in contrast to the traditional one-way journey from a single Big Bang to eventual heat death. Instead, the multiverse becomes an eternal, self-sustaining cycle of creation and destruction. Universes beget other universes through their black holes. A star collapses in a parent universe, giving birth to a child universe inside the resulting black hole. That child universe expands, forms its own stars and galaxies, and those stars eventually collapse into black holes, each one spawning its own new universe in an endless, magnificent fractal. Our own Big Bang, in this view, might not have been a singular beginning from nothing, but rather the white hole output of a black hole formed in a previous, larger universe. The mathematical foundation for this is more robust than one might assume. When you examine the equations describing the gravitational collapse of a star into a black hole and the equations describing the expansion of the universe from a Big Bang, they are strikingly similar. In both cases, you have a geometry of spacetime that is evolving from a state of low density to a state of extreme density, or vice versa. For an observer inside the new universe, their reality begins with a hot, dense state that is expanding. It looks exactly like a Big Bang. For an observer in the parent universe, they simply see a black hole forming. The same event is described by two completely different perspectives, with neither being more correct than the other. This duality gives the theory a compelling elegance and symmetry that many physicists find deeply attractive. The implications of this theory are staggering to contemplate. It would mean that the fundamental constants of our universe, the strength of gravity, the mass of an electron, the value of the cosmological constant, might not be random, arbitrary numbers. They could be inherited properties passed down from the parent universe whose black hole we formed within. This could offer a potential explanation for the infamous fine-tuning problem, the observation that our universe's constants appear perfectly calibrated to allow for the existence of life. If universes are born within black holes, then it's possible that only those with the right constants can produce stable stars and planets, which in turn produce more black holes and spawn new universes that inherit those same constants. In this way, life-friendly universes would be naturally selected for across cosmic generations. Of course, the profound challenge is that these child universes are, by their very nature, completely cut off from our own. No information, no light, no signals can cross the boundary from the inside of the black hole to the outside. we could never observe our parent universe, and we could never peek into the universes being born within the black holes in our own cosmos. This makes the theory incredibly difficult, if not impossible, to test through direct observation. However, some theorists suggest that if our universe was born from a specific type of black hole in a specific type of parent universe, it might have left a faint imprint on the pattern of the cosmic microwave background radiation, the afterglow of our own Big Bang. Finding such an imprint, perhaps an unusual pattern of polarization or temperature fluctuations, would be the first tantalizing clue that our cosmos is not all there is, but merely one link in an infinite chain of cosmic creation, where every black hole is a door to a new reality, and every universe is a seed within another. Yet if the universe itself is a grand cycle of birth and rebirth through black holes, the sheer energy involved in these processes is almost beyond comprehension. But what if there was a way to tap into that power directly, not by destroying a black hole, but by borrowing energy from its very spin? This brings us to a remarkable and highly efficient cosmic energy extraction method known as superradiance, a process where a rotating black hole can be convinced to amplify waves and particles, effectively acting as a gigantic battery for any civilization advanced enough to plug in. The engine for this incredible phenomenon is the black hole's rotation. A spinning black hole, known as a Kerr black hole, doesn't just warp space, it drags it around in a powerful whirlpool effect, a region just outside the event horizon called the ergosphere. Within this ergosphere, something truly bizarre happens. It becomes impossible for any object to remain stationary. Everything is forced to move in the direction of the black hole's spin. But this frame dragging also creates an opportunity. Imagine sending a wave, be it of light or even just a gravitational ripple toward this rotating monster. If the wave has a specific frequency, one that is lower than the rotation rate of the black hole itself, a peculiar quantum effect can occur. When the wave enters the ergosphere, the rotating spacetime can actually impart energy to it. The wave steals a tiny amount of the black hole's rotational energy, gets amplified, and then escapes back out into space, brighter and more powerful than when it went in. It's like throwing a tennis ball against a moving treadmill. If you get the angle and speed just right, the treadmill can fling the ball back at you with even more energy than you gave it. This isn't just a minor amplification. Through a process called the Penrose process, named after physicist Roger Penrose, who first proposed it in 1969, this could be scaled up to extract significant amounts of energy. In theory, an advanced civilization could feed particles or waves into the ergosphere of a suitably large, spinning black hole. The black hole would act as a catalyst, weakening its own spin slightly while supercharging those particles, which could then be captured by a surrounding Dyson sphere-like structure. The efficiency of this conversion could be extraordinarily high, far surpassing any nuclear fusion or antimatter reactor we could ever conceive of building. A single stellar mass black hole could provide the power needs of a galaxy spanning civilization for eons, simply by slowly breaking its rotation. The universe itself might already be putting on a show of superradiance on a colossal scale. Theorists propose that clouds of ultralight hypothetical particles like actions could form around a spinning black hole. These particles would constantly interact with the black hole's ergosphere, getting amplified through superradiance and building up into a gigantic, invisible cloud that orbits the black hole like a fuzzy quantum halo. This cloud could contain a significant fraction of the black hole's own mass, acting as a storage system for its rotational energy. Eventually, this energy could be released in a spectacular burst of gravitational waves when the cloud becomes unstable and collapses back into the black hole. Observatories like LIGO and Virgo could one day detect these unique, long-lasting gravitational wave signals, providing indirect but powerful evidence that this incredible energy transfer is not just theory, but a natural part of the cosmic dance. Yet if black holes are the ultimate quantum computers as we just explored, processing information with unmatched efficiency, then we must ask what the physical hardware of such a system would actually look like. This leads us to a theory that radically reimagines the event horizon itself, transforming it from a perfectly sharp, classical boundary into a dynamic and blurred region where quantum uncertainty reigns supreme. The idea of fuzzy black holes challenges one of the most fundamental assumptions in Einstein's theory of general relativity, the notion that the event horizon is a perfectly defined, one-way surface in spacetime. In the classical picture handed down to us by relativity, the event horizon is a mathematically precise boundary. It's the point of no return, a smooth and uneventful gateway where the inward pull of gravity becomes so strong that not even light can escape. For an astronaut falling in, crossing this horizon would be a local non-event. They would feel nothing special at the moment they passed through. But this clean, classical picture completely ignores the bizarre rules of quantum mechanics, which tell us that at the very smallest scales, nature is inherently fuzzy. Particles can be in two places at once, energy can fluctuate wildly, and perfect certainty is impossible. So how can the universe maintain a perfectly sharp, two-dimensional surface around a black hole when the fundamental fabric of reality is inherently blurry? This is where the theory of quantum geometry comes into play. In attempts to formulate a theory of quantum gravity, such as loop quantum gravity, spacetime itself is not smooth and continuous as Einstein described. Instead, it is thought to be granular or discrete, made up of tiny, indivisible units at the Planck scale. Think of it like a digital photograph. From a distance, the image looks smooth and continuous, but when you zoom in to the pixel level, you see the individual blocks that make up the whole. In this quantum description, the event horizon cannot be a perfectly sharp surface because spacetime itself is pixelated. It would have a kind of texture or fuzziness, a region where the very definition of inside and outside becomes smeared over a small volume due to quantum fluctuations. This fuzziness could manifest in several extraordinary ways. One possibility is that the horizon is not a static shell but a seething, turbulent region of virtual particles constantly popping in and out of existence, a quantum froth so intense that it blurs the precise location of the boundary. Another idea is that the horizon possesses a finite, though incredibly small, thickness. Instead of a mathematical line, it would be a transitional zone where the properties of spacetime gradually change from those we understand to those we don't. An object falling into a fuzzy black hole wouldn't cross a definitive threshold at a single moment. Its passage would be a gradual process of becoming increasingly disconnected from the external universe, much like fading into a thick fog rather than stepping through a door that instantly slams shut. The implications of this quantum fuzziness are profound, especially for the infamous information paradox. If the horizon is fuzzy, then information from the outside might not be completely severed from the inside in one catastrophic moment. There could be a prolonged interaction, a quantum dialogue between the interior and exterior that allows information to be exchanged or encoded in a more complex way. This could provide a natural mechanism for information to be preserved and eventually returned via Hawking radiation without the need for a violent firewall. The black hole's quantum computer would have a slightly blurred interface with the rest of the universe, allowing for a more seamless flow of information processing. Testing this theory is a monumental challenge as the scale of this fuzziness is unimaginably small, on the order of the Planck length. However, future observations might provide indirect clues. Extremely precise studies of the gravitational waves from merging black holes could one day reveal subtle deviations from the predictions of classical general relativity. If the event horizons are truly fuzzy, the moment of merger might produce a slightly different gravitational wave signal than if they were perfectly sharp. Furthermore, if we ever manage to observe the immediate environment of a black hole with even greater resolution than the Event Horizon Telescope, we might detect hints of this quantum blurring at the edge of the shadow it casts. While these measurements lie far in the future, the very existence of the theory forces us to confront the beautiful and complex reality that the universe's most extreme objects are not the simple, smooth pits we once imagined, but are instead the ultimate expression of a reality where nothing, not even the point of no return, is ever perfectly defined. Yet for all the power of these cosmic engines, the most critical question remains: what happens to the story of everything that falls in? If a black hole evaporates away to nothing, does the narrative of a star, a planet, or a spaceship simply vanish from the cosmic library? This brings us to a theory that has moved from a fringe possibility to a leading contender in solving physics' greatest puzzle. The idea is that the information isn't lost at all. It's imprinted onto the Hawking radiation itself, encoded in the most subtle of quantum whispers. For decades, the information paradox presented a seemingly impossible choice. Stephen Hawking's initial calculation showed that the radiation leaking from a black hole was purely thermal, a featureless hiss of random heat. It carried no more information about what fell in than the warmth from a fireplace tells you which specific logs were burned. If this was the final word, then the unique quantum identity of every particle swallowed was erased forever, violating a fundamental tenet of quantum mechanics. Yet the alternative, a deadly firewall at the event horizon, shattered the cornerstone of general relativity, the principle that an astronaut crossing the horizon should feel nothing special. Physicists were trapped between two pillars of modern physics, forced to choose which one to break. The potential resolution is as elegant as it is complex, and it lies in the bizarre quantum phenomenon of entanglement. In the quantum world, two particles can become deeply linked or entangled, such that measuring the state of one instantly determines the state of the other, no matter the distance between them. Now apply this to the creation of Hawking radiation. Remember that the radiation is produced when a pair of virtual particles pops into existence at the edge of the event horizon. One particle falls in while its partner escapes. In the standard picture, these two particles are entangled with each other. But here's the catch: the particle that falls in becomes entangled with the interior of the black hole itself, with all the matter that has already been consumed. This creates a terrifying problem called the monogamy of entanglement, a rule which states that a quantum particle cannot be fully entangled with two different systems at the same time. This is where the concept of quantum correlations offers a breathtaking escape route. The proposal is that as the black hole evaporates, the intricate web of entanglement doesn't just break, it transfers. The information about the interior is not carried away on individual radiation particles like a message written on a series of separate postcards. Instead, it is encoded in the subtle correlations between the particles of Hawking radiation. It's the difference between trying to understand a story by looking at a single, random word from each page and being able to see how all the words on all the pages relate to one another. The story is not in the words themselves, but in the pattern of their connections. This process is often described as the information being scrambled and then gradually unscrambled as the radiation is emitted. The black hole acts like a cosmic blender, taking the ordered information of the infalling matter, churning it into an apparently disordered spray of particles, but doing so in a way that preserves all the original data within the overall pattern. Testing this theory is a formidable challenge, as detecting these specific quantum correlations in the faint Hawking radiation from an astrophysical black hole is far beyond our current technology. However, physicists have found ingenious ways to simulate the principle in the lab using analog systems. One remarkable experiment involved creating a sonic black hole in a superfluid. In this setup, sound waves rather than light waves cannot escape a specially designed region mimicking an event horizon. Researchers were able to measure the resulting Hawking radiation of sound waves and, crucially, detect the telltale quantum correlations between the paired phonons that were created. While not a perfect replica of a gravitational black hole, These experiments provide strong supporting evidence that the underlying quantum mechanics is sound and that information can indeed be preserved in this way. If this theory holds, it paints a beautiful and complete picture of a black hole's life cycle. It begins as an information vacuum cleaner, sucking in matter and all its associated quantum data. During its long life, it functions as the ultimate quantum computer, scrambling and processing this information. Finally, in its old age, it transforms into an information fountain, faithfully returning every bit of data back to the universe encoded in the correlations of its final evaporating burst. The black hole doesn't destroy the past, it translates it into a new quantum language, ensuring that no chapter of the universe's history is ever truly lost. But for all their power to destroy, could these cosmic monsters also be the ultimate creators? This brings us to a theory that turns the terrifying image of a black hole on its head, casting it not as a grim reaper for worlds, but as a potential catalyst for life itself. It's a profound paradox. The same gravitational pits that devour stars might also be the unseen architects that make galaxies habitable and provide the very elements necessary for biology to emerge. Let's start on the grandest scale, the galaxy. A supermassive black hole sitting at the heart of a galaxy is not just a passive ornament, it's an active regulator. As it feeds, it doesn't do so quietly. The immense energy released from its accretion disk in the form of powerful jets of radiation and particles can blast out across the entire galaxy. This might seem purely destructive, and it can be, but this energetic feedback also plays a crucial role. It can heat up enormous reservoirs of gas, preventing it from cooling and collapsing too quickly to form a frenzy of new stars. Without this regulatory pressure, a galaxy might burn through its stellar fuel too rapidly in a short, intense burst of star formation, leaving behind a quiet, aging population of stars with few heavy elements. By pacing the process, the central black hole helps to create a stable, long-lived galactic environment where star formation can proceed at a steady rate for billions of years, providing the long-term stability that is likely essential for the slow, gradual evolution of life on planets orbiting those stars. Furthermore, the chaotic environment around an active black hole might be a surprising cosmic forge for the building blocks of life. We know that the heavy elements essential for life, like carbon, oxygen, and iron, are created in the furnaces of stars and scattered by supernova explosions. But the accretion disks of supermassive black holes are even more extreme environments. The densities and temperatures there are so astronomically high that they could facilitate nucleosynthesis, the creation of new atomic nuclei, through processes we can scarcely replicate. Atoms could be slammed together with incredible force, forging elements even heavier than iron, which are normally only produced in the most violent supernova or neutron star mergers. These newly minted elements would then be ejected by the black hole's jets or winds, seeding the surrounding galactic regions with a rich and complex palette of chemistry. The iron in your blood and the calcium in your bones may have been born in a star, but some of the rarer elements around you might have had their origin in the incredible violence surrounding a feeding black hole billions of years ago. Looking even further into the far future, black holes could become more than just silent partners. They could be the ultimate power stations for civilizations that have outlived their stars. As the universe continues to expand and cool over trillions of years, stars will eventually burn out, leaving the cosmos a dark and cold place. But black holes will remain, and for any surviving intelligent life, they would be the last concentrated sources of energy in an otherwise dissipating universe. An advanced civilization could harness this power through incredible feats of engineering. One theoretical method is the Penrose process, where objects are sent into the ergosphere of a spinning black hole and broken apart, with one piece falling in and the other escaping with more energy than it entered with. Another, even more ambitious concept is to build a Dyson sphere not around a star but around a black hole. A black hole accretion disk can be heated to temperatures of millions of degrees, emitting not just light but powerful X-rays. By surrounding it with a capturing structure, a civilization could extract this energy. They could even feed the black hole with carefully collected interstellar matter, like throwing logs on a fire, to keep their energy source running for eons longer than any star could ever last. In the absolute twilight of the universe, a black hole would be the final beacon of power and warmth, potentially allowing life to persist long after the last star has flickered out. But perhaps the most profound connection lies not in travel, but in creation itself, tying back to the black hole cosmology theory we explored earlier. If our universe was born from a black hole in a parent cosmos, then the physical constants that govern our reality, the strength of gravity, the mass of an electron, the value of the cosmological constant, might not be random, arbitrary numbers. They could be inherited properties, cosmological DNA passed down through the generations. This offers a potential and deeply elegant solution to the infamous fine-tuning problem. The reason our universe's constants appear perfectly calibrated to allow for stars, planets, and life might be a form of natural selection on a multiversal scale. Only those baby universes born with stable constants can form long-lived stars and galaxies, which in turn produce more black holes that spawn new universes with similar constants. Universes that are not life-friendly simply fail to reproduce. In this breathtaking vision, black holes are not just bridges between worlds. They are the engines of a cosmic evolutionary process, weaving a vast, fractal tapestry of realities where the conditions for life are not a miracle, but an inevitable outcome of a timeless cycle of birth, death, and rebirth. From the mind-bending potential of wormholes offering cosmic shortcuts to the startling revelation of Hawking radiation slowly evaporating them away, our journey has taken us to the very edge of theoretical physics and beyond. We've grappled with the paradox of information screaming to be lost forever within their depths, and explored radical alternatives like gravastars and Planck stars that seek to avoid the infinite despair of a singularity. We've considered the possibility that these dark giants could be the very source of dark energy, the hidden architects of galactic habitability, and even the progenitors of entirely new universes, with every black hole a potential big bang for a reality beyond our own. The sheer range of ideas, from quantum hair preserving a memory of everything they consume to the wild notion of black hole atoms, and the ultimate computational power they may possess, paints a picture of objects that are infinitely more complex and fascinating than simple cosmic vacuum cleaners. What makes black holes so eternally compelling is that they are the universe's greatest paradox. They represent a brutal simplicity describable by just 3 numbers, yet they simultaneously contain complexities that force us to question the most fundamental laws of nature. They are the ultimate testing ground, the place where our 2 most successful theories, the grand cosmic scale of general relativity and the fuzzy, probabilistic world of quantum mechanics, meet and violently disagree. Each new theory, from the holographic principle to the search for gravitational wave echoes, is a testament to human curiosity and ingenuity, a desperate and brilliant attempt to listen to the universe's whispers and piece together a story that makes sense. They don't just challenge physicists, they challenge our very perception of reality, asking us to accept that space might be a projection, time might be malleable, and that the darkest points in our sky might be the brightest beacons for understanding everything. This conversation is far from over. Every new observation, every gravitational wave signal, and every sophisticated new simulation brings us closer to potentially confirming one of these incredible ideas or discovering something entirely new that will rewrite the textbooks once again. The mystery is what keeps us looking up and wondering. Now we want to hear from you. After this tour of the theoretical extremes, which idea captured your imagination the most? Do you think wormholes are traversable gateways, or is our universe just one bubble in an infinite multiverse born from a black hole? Share your favorite theory in the comments below. We love diving into these discussions with you. If you enjoyed this deep dive into the unknown, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the cosmos's greatest mysteries.